Welcome to the class Advanced Solid State Physics 1. So this is the first day of our lecture, and this course is given in English. So I hope everyone could understand my English reasonably well, even though I'm not a native speaker, but I think you are able to understand what I said. So first of all, this is advanced solid state physics. So in other words, this is not an introduction to solid state physics. So let me ask you this question. So if you have not taken any introductory level of solid state physics, please raise your hand. Yeah, okay, good. So, and for those of you who have not taken introductory level of solid state physics, I think you will have some trouble understanding, at least some of the lectures that I'm going to tell you about. So I encourage you to also either to sit in this introductory level of solid state physics, or you will take the introduction to solid state physics at the same time, at least. Okay, another question, if you have not taken introduction to quantum mechanics or quantum physics, you have no knowledge about any quantum mechanics, please raise your hand. Okay, and again, this course may not be suitable for those of you who have not taken any introduction to quantum mechanics, because we are about to study solid state physics, which is based on quantum mechanics, many particle system, and also some basic knowledge in introductory level of solid state physics is necessary. So you could still register this course, but more or less you will feel some trouble as time goes by. And if you feel that you have really difficulty in understanding, and you will know what you can do. Namely, you can drop the course. All right? So don't drop the course until very end of the semester. It's too late. So the prerequisites for this course are twofold. One, some knowledge of introduction to solid state, and some knowledge in quantum mechanics. And of course, some knowledge in statistical physics is also important, okay? Because we are trying to understand, many particle systems in the region where the quantum mechanics dominates, okay? Such as insulators, metal semiconductors, and magnets, and so on, superconductors, things like this. And so the knowledge in these three branches of physics is really important, some knowledge. So if you have not taken quantum mechanics of the graduate level, that's fine, but at least you know something about Schrödinger equations, and the probabilities, scatterings. And for the statistical physics, you should have known fermions and bosons, okay, spins, angular momentum. So that's for quantum mechanics. And for this introductory level of solid state physics, you should probably have known the Fermi surface, energy gap, bands, something like this. So once again, this is advanced level of solid state physics. So the topics will be more or less what you have learned in the introductory level of solid state 1, but we will learn the new technique called the second quantization approach, which is kind of a very elegant mathematical way to understand what you already learned in introductory level of solid state physics. So the content will be given in just a moment. So I hope that all of you could actually understand what I'm going to tell you this semester. So this will be fun because you will learn a completely new technique and new perspective to the phenomena that you may or may not have heard about this before. And these are our textbooks or reference books. The first one is the most, I should say, one of the major references is this. It's called Many-Body Quantum Theory in Condensed Matter Physics, an Introduction. Okay, so this is a major reference book which introduces the second quantization and also all these topics that we will study. And the second useful reference is this Quantum Theory of Solids, written by Charles Kittel. And Charles Kittel also wrote another very famous textbook, which is Introduction to Solid-State Physics. So this is the major textbook when you study Introduction to Solid-State Physics 1. Okay, but we are going beyond that book. Of course, we will cover many chapters in the Introduction to Solid-State Physics, but we are going beyond that. We are not just staying this level. We are beyond that level. And also a very important lecture notes written by David Pines, which is a well-known condensed matter theorist. And he wrote this lecture notes many decades ago, like 1960s. So it is out of print. This is called Elementary Excitation in Solids. We will also take part of his lecture notes to actually study when we talk about this electron-hole pair excitations in solids. So this is about the textbooks. Good. So let's talk about what we are going to learn this semester. Again, as I mentioned, this course is about using second quantization to solid state. At this point, you don't understand what I mean by second quantization. I will tell you more details later. But in any case, we try to learn a new technique called second quantization, which allows us to count the particle number, because we are dealing with millions and millions of particles, atoms, electrons in solid state. So a systematic way to count the particle number is necessary. And the second quantization approach is the only way that we can manage to understand solid-state physics in a systematic way. Okay, so this is the key. So the content of the solid-state physics is no more than what you already learned in the introduction level of the solid state. So first of all, I will give you a very short review of the basics in solid-state physics, especially the interactions in solids and elementary excitations and quasi-particles. So again, I will give you a very brief introduction or review of the fundamental aspects of the solid state 1, which include interactions in solids, namely Coulomb interactions, and also the excitations above the ground state, low energy or low temperature excitations of those solid state systems. And we will emphasize the elementary excitations. What are the elementary excitations in solids or quasi-particles? So you may have heard about these names, but you may not understand what these are. But these two terms become very important in the advanced solid-state physics, because all this low temperature, low energy physics in solids come from those elementary excitations or the quasi-particles. So what are the quasi-particles? Well, they are not real particles like electrons or photons, but they carry quantized energies, and they are not real particles, so they are called quasi-particles. So these quasi-particles are the low energy excitations above the many-body ground state. So we will talk about this introduction to this concept. These concepts are new to all of you, I believe. But this is the center part of the solid state, which are all about quasi-particles and elementary excitations. So in other words, this elementary excitation solids, written by David Pines, is the heart of our course. Namely, through the semesters, we're all talking about this elementary excitation and quasi-particles in different systems, fermions and bosons and so on. Okay, so this is the review. Then I will continue talk about electron-electron interactions in metals. In particular, we will introduce the second quantization of fermions. So I suppose everyone knows that in solid-state systems there are two types of materials. One is called fermions, another is called bosons. Or from your periodic table, you know that half of the atoms shows integer spin, which are called bosons, and another half integer spins, which we call fermions, right? So in the first chapter, we will discuss the fermions or electrons in metals, and we will introduce how to count electron number by second quantizing the electron operator, so that we can count how many electrons in there, at low temperatures or energies when we talk about the elementary excitations. And then we will employ the approximation called the Hartree-Fock to actually study the electron-electron Coulomb interactions in solids or in metals. Study electron Coulomb interactions in metals. Again, so the first few chapters addresses the physics of metals, and you are already familiar with metals. Not quite, because say non-interacting electrons in metals are really well understood, but the more difficult, the challenging task is to include the Coulomb interactions in metals, which will lead to some problems and troubles. And so that's what we will discuss in this class, right? So all these easy materials, such as non-interacting metals, are just introductory level of solid state, but we will take the challenge to include the Coulomb interactions. Once we include the Coulomb interactions, then we find many troubles and difficulties, and we should try to overcome such problems. And so this is the one of the purpose of this course. And then later we will introduce perturbation theory. So the Hartree-Fock approximation fails to describe the Coulomb interacting electron gas in metals. So we will go beyond the Hartree-Fock, which is mean field-like approximations, and do perturbation in quantum mechanics, and employ a different technique called the random phase approximation, which is another approximation, but in the perturbative way. So we will introduce such a technique to actually overcome this trouble caused by the Hartree-Fock failures. In other words, even electron-electron Coulomb interactions in metals is a difficult task. So we know that electrons repel each other in metals, but how to really accurately account for such a effect is not an easy task. So we'll come from the first step, which fails, and then we learn from our failures, and we will try another method, which may or may not work. And hopefully they work. And we'll introduce this density operators in the second quantization scheme. And this electron density operators in the second quantized formalism is the proper language. Okay, so we will talk about that. And using this proper language, we are able to describe many phenomena in metals, such as plasma oscillations, such as dielectric response, such as Coulomb screening of electron-electron Coulomb interactions. So this is the logic. Once we found the correct language or the proper approach, and we could use that language to systematically describe all the phenomena that we can find in metals, such as these plasmons, dielectric properties, and Coulomb screening of electron-electron interactions in metals. So in other words, all this, the first few chapters of our course deals with the Coulomb interacting electron gas in metals. And if we don't find a good starting point, and we cannot describe those phenomena in a more accurate way. Okay, so here we introduce second quantization to count the electron number in low temperature, low energies, and we are able to describe such phenomena in a more systematic way. But some of you may have already learned this physics in the introductory level of a solid state, but those knowledge is not deep enough. So we introduce this second quantization approach, which allows us to more deeply and more systematically address those phenomena that you may or may not have heard about this at the introductory level of a solid state. So the phenomena that we are going to describe is nothing more than the introduction to solid state, but the method is new. So we employ a completely new concept to understand the phenomena that we have heard at elementary level of a solid state. It's a new package. Okay, so this is the purpose, and this is actually the part 1. It's about metals, and part 2 is about bosons. As I mentioned, there are two kinds of particles in nature. One is called fermions, another is bosons. And at the very beginning of our course, we discuss fermions, such as metals, because in metals, the most important particles are electrons, and electrons are fermions. So we learned how to count the electron numbers by second quantization of fermion operators. So now, after studying these fermions, we focus on these boson systems. So we try to second quantize the boson operators. So the examples of bosons in nature include photons and phonons and magnons and plasmons. So we will study all these different bosonic quasi-particles later. So, but apart from photons, so the photons are real particles. They are light electromagnetic waves, but phonons, magnons, and plasmons are all quasi-particles. They are not real particles, but they consist of very important elementary excitation solids because they carry quantized energies in h bar omega, where omega is the frequency. And so you could actually count how many bosons or phonons are there in your systems by counting, the boson number. And how to count the boson number? We will introduce a way to count the boson number, so that you could count how many phonons are there in your solid state systems and how many magnons, which are responsible for the magnetic excitations of magnetic materials, and or the plasmons, which is just kind of electron hole pairs. But then we would deduce this basic phenomena of the bosons, which is called BEC, which says that bosons at ground states would like to get together to form a macroscopic huge wave functions called matter waves. And this phenomenon is called Bose-Einstein condensation, which means that the bosonic wave functions like to overlap, and they're, unlike the electrons or fermions, they have the Pauli principles that two electrons can occupy in the same states, right? But two bosons, or as many bosons as possible, they like to get together to form a huge macroscopic matter wave. It's called the Bose-Einstein condensation. When T is less than this TBEC, all these bosons like to, just group together. They like to come together and to form a huge macroscopic wave function. And we'll introduce this phenomena. And then we will discuss each of the individual bosonic excitations. For example, these phonons, which are the quasi-particles due to lattice vibration. Again, we will discuss how the lattice, the ions vibrate, and how this vibration of the lattice will lead to this phonon, which is a quantized energy due to the lattice vibration. All right, and then we'll introduce all these properties of phonons in the Debye model, for example, and also phonon-phonon interactions. Okay, so we need the phonon-phonon interactions to really reach the thermal equilibrium in any thermodynamic processes in solid state. But again, so all this study relies on second quantization of bosons, because the boson and fermions satisfy different statistics, right? So the fermions satisfy this Fermi-Dirac, but bosons satisfy Bose-Einstein statistics. So I think time is up for today, but we haven't finished introduction to the outlined introduction of this course, but we will finish the outline of the course on Wednesday. Okay, so we'll start from here and we'll continue to introduce what topics that we will introduce for this course. So these terminologies and those special terms for you is just a term for now, but later at the end of the semester you will be able to really understand what it means physically. So if you don't understand this, that's 100% fine, because these topics are for you to understand for the whole semester. So I'm just telling you what topics that we will cover in this course. So what kind of physics that you will learn. So you will learn those physics in this course by second quantization approach.